We've looked at analyzing and the properties of rational functions. Now we're going to put those into action to actually graph some rational functions without using a calculator. Or at least a graphing calculator. And that's the whole point of this. So we begin by a relatively simple rational function, as you see here. R of x is equal to x minus 1 divided by x squared minus 4. Step one is always to factor the numerator and the denominator to make sure, one, that it's in lowest terms, that it's reduced, because we can't make decisions until we know it's in reduced form. So then we find the domain after we have the denominator factored as well. So you see here we've got the denominator factor. The numerator is already in factored form. It's as simple as it can be put. So we know what the domain is. It's the set of all x's such that x is not equal to -2 and x is not equal to +2, because those are the two values of x that would cause the denominator to be equal to 0. And we know that that also has some additional meaning to us, because that's also tells us something about where the vertical asymptotes will be. Well, it's in the lowest terms, as we've already mentioned. So we'll need to locate the intercepts, and there are, of course, two types of intercepts. There are y-intercepts, potentially, not always do they exist, and there are x-intercepts, potentially, not always do they exist. But the way we find y-intercepts is we let x be equal to 0. And so we put 0 into the function for x, and we calculate y. And you can see here, if we put a 0 in for x, we'd end up with -1 over -4, which is +4. So the y-intercept has an x value of 0 and a y value of 1/4. Now, to find the x-intercepts, we let y be equal to 0. And y, of course, let's keep in mind, y is really this r of x. Okay? So if that's 0, we have 0 is equal to this fraction. Well, as we go to solve that in equation, we'd find by multiplying both sides by the denominator, we'd end up with 0 is equal to x minus 1. And that should really tell us something pretty important. The only way a fraction can be equal to 0 is if its numerator is 0. You know, if its numerator is not 0, then we're going to have some non-zero number divided by some non-zero number, and that can't be 0. So we'll always come to this point where we have the numerator equal to 0 is when we're trying to find x-intercepts. In this case, the only solution to that is x being 1, and so the x-intercept is where x is 1, and y is 0. So we have 2 points that we can graph now. Here we had x is 0 and y is 1/4, our two intercepts. Okay. Well, let's locate the vertical asymptotes, and because we already had that denominator in factored form previously, we knew that we had a vertical asymptote at x equal -2 and x equal +2 from work we've done in the previous section. And we locate the horizontal asymptotes or oblique asymptotes. In this case, we look, remember how we do that. We look at the degree of the numerator and we see that degree is 1. When we look at the degree of the denominator and we see that degree is 2. And so whenever the degree of the numerator is smaller than the degree of the denominator, then there is a horizontal asymptote, and it's simply the line y equals 0, which is the x-axis. So we plot or graph with dashed lines our two vertical asymptotes. Here's the vertical asymptote x equal -2 and the vertical asymptote x equal +2. And the horizontal asymptote y equals 0, okay, which matches with the x-axis. And then you see that we have plotted the two intercepts. The y-intercept is right here, okay, and the x-intercept is right here. Plotted both of those. Okay, well, what do we do next? Well, we need to calculate and plot some additional points that are between x value that have x values between the vertical asymptotes and any x-intercepts. So for instance, let's back up a step. See, here we have a vertical asymptote, but we're not using any x values out here. Here we have a vertical asymptote, and here we have a x-intercept. We're already using one x value, x equals 0, between those two. Now, we do not have any x values used between this x-intercept and this vertical asymptote, and we have no x values out here beyond this asymptote. The reason we want to do that is we want to know where the graph is out here. Is it down below or is it up above? And in this case, let's just imagine we might have this graph actually going up right here, mightn't we? Or it might go down. Now, that little segment in there makes it look like it's going down, but in advance we don't know that. And so we need an x value between 1 and 2 that will tell us, are we way up here, or are we way down here? And likewise out here in this region, we need to know if our graph is in this part of the plane or is in this part of the plane. So that's the reason we do that. Okay, well, let's go back and let's plot some additional points. So I took -3, which is to the left of this vertical asymptote. I took an x is equal to -3 and got a y of -0.8 and plotted that point. And then I took an x value between 1 and 2. See, an x value in here between this x-intercept and this vertical asymptote. So I chose 1.5 or 3/2, and I calculated a y of -2/7. And so I plotted that point. Now we have an idea of what's going to happen. And then I took an x value that was to the right of this vertical asymptote, x value of 3, and I calculated the y value and got 0.4. And I plotted that point. Now, here's the idea. We know already, well, let's go to the next slide. We're going to analyze the behavior near each of those asymptotes and get an idea of what the graph is going to look like. And so here's what I was getting at. We know that we have this point, okay? But we know that the further we go out to the left, the closer the graph has to get to the horizontal asymptote. So it's going to go something like that. And we know when we get close to a vertical asymptote, the graph has to either go down or it has to go up. And the reason we know it doesn't go up is because this is the only place it crosses the x-axis right here. That was the only x-intercept. Okay, so it can't go up, it has to go down. So that kind of gives us what this shape is going to look like. Now let's move over here to the right, the same kind of thing. We know if we go way out to the right, the graph is going to have to get closer and closer to that horizontal asymptote. And we know when we get close to a vertical asymptote, the graph has to either go up or it has to go down. But we know it can't go down here because that would require us to have another x-intercept, and we only have this one right here. Okay, well, in the middle, we have these 3 points. And we know, for instance, that as we get close to a vertical asymptote, the graph either goes down or goes up. And we know it's not going to go up from this position as we've done before because there's only one x-intercept, and that would require another one. And likewise here, from this point, it can't go down. It has to go up because if it went down, there would be another x-intercept, and we've found all those. And so we kind of have an outline of what this graph is going to look like now, don't we? And so that's what we do next. We just sketch it in using that analysis that we've just completed, and that's what our graph would look like. Okay, well, let's move on to another one. Analyze and graph the rational function that we have here, which is r of x is equal to x squared minus 1 divided by x. So once again, we factor the numerator and denominator. And in this case, it's in factored form here on step 1. And then we can tell the domain because the domain is all the values of x for which the function is defined. And it's only undefined if the denominator is 0. And that's going to also give us a vertical asymptote through x equals 0, isn't it? Okay, so we know it's in lowest terms, so we can move on now to do the other things. And and what would we be doing next? We would be looking for intercepts. And in terms of a y-intercept, remember, here's the big deal. For a y-intercept, x has to be 0. But since x can't be 0 here, that means there is not going to be a y-intercept. So this graph's never going to cross the y-axis. In fact, and that's where x is equal to 0. In fact, we're going to have a vertical asymptote there. Now, the graph has two x-intercepts. How would we do that? Well, remember, we would set y to be equal to 0. And so we would have 0 is equal to this fraction. But the only way a fraction can be 0 is if its numerator is 0. And this numerator can be 0 if x is either -1 or +1. So that's how we make this decision. So we have two x-intercepts. One is where x is -1 and y is 0. And the other one is where x is +1 and y is 0. Okay? So we've plotted those two intercepts. Okay? And we can next go ahead and put in our asymptotes that we've already determined. Remember, we had an asymptote of x equals 0 because that's the value of x that causes the denominator to be 0. Okay. Now, what about horizontal asymptotes? Well, look here. The degree of the numerator is 2, and the degree of the denominator is 1. It's 1, not 0. Okay. And whenever the degree of the numerator is more than the degree of the denominator, there's not a horizontal asymptote. But in fact, if the degree of the numerator is exactly 1 more than the denominator, then there's an oblique asymptote, or a slanted asymptote, sometimes called. And so how do we find that? We take the denominator and we divide into the numerator. And that's what I've done here. And then we look at the quotient when we get finished doing our division. Because the remainder is -1, we can't go further, and the quotient is x. And so this slanted asymptote or oblique asymptote is y equal to that quotient, x. So y equal x is our oblique asymptote, as I've said here a little more formally. And that's the line y equal x. Now remember, here are two x-intercepts also plotted. Okay, our two x-intercepts plotted, and our vertical asymptote right here, and our slant asymptote or oblique asymptote right here. Well, here's what we would do next. Same as we've done before. We would find some values between the intercepts, okay, between the intercepts and beyond the intercepts, between the intercepts and any vertical asymptotes, not slant asymptotes, any vertical asymptotes. To decide what this graph is really going to look like. So we calculate a few additional points. Okay, so here's what I've done. Remember, here is our vertical asymptote, here is an x-intercept, and there's nothing beyond this x-intercept, so I chose an x value of -2 and calculated the y value, and I got this point. Now, here is that x-intercept again. But here's the vertical asymptote, and I didn't have a value in between there, so I chose a value of -1/2. And by the way, how am I doing this? I mean, remember, all I'm really doing is I'm calculating y using this formula. And so if I choose x to be -1/2, it's going to be -1/2. That's a -1/2, not a -7/2. Sorry about that. Squared minus a 1 for the numerator and a -1/2 for the denominator. And when we calculate that, we get a positive, sorry about that, also very ugly, 3/2. And so that's where this point came from. And then we do a similar thing to the right of this vertical asymptote. We look between the vertical asymptote and the x-intercept, and we choose an x value that's between there, an x value of 1/2, and calculate the y that goes with it, just as we did on the other side. And then we go beyond this x-intercept. There's nothing stopping us on the right, so we need one more x to the right, and I chose an x of 2 and calculated the y that went with that, and it gave me this point. And so now we can kind of see, because we know, here's what we know. If we go close to a vertical asymptote, the graph either goes up or down, and it can't go down here just as we did before, because that would create another x-intercept. And when we go out to the left or go out to the right, the graph has to get close to the, in this case, slant asymptote, and so that's the reason we're showing it as we see it here. And likewise out here, it has to get close, and it has to go down here because it can't go it can't go up from this point, because remember, when we get close to a vertical asymptote, and here, when we're getting close to a vertical asymptote, it's got to either go down or up. Can't go up because there'd have to be another x-intercept. So we get the shape of the graph pretty easily that way. And so we'll go ahead and fill that in, and there's actually what the graph will look like. Okay. Remember, you can slow this down or back up this video, and you may need to do that because occasionally I get to going pretty fast. Now, this next rational function we want to analyze and graph. And as before, the first thing we need to do is factor numerator and denominator, mainly to see whether it's in reduced form. And when we do here, we see that it is, in fact, in reduced form. So what do we do next? Well, then we're ready to find intercepts. And so how do we find a y-intercept? We let x be 0. So we put a 0 in for x. And notice when we put a 0 in for x up here, this will give us 3 times 0 minus 3 times 0. So the numerator is 0 and the denominator is negative 12. So if x is 0, then the y is 0 over negative 12, which is just 0. So that's the y-intercept. Now, on the other hand, if we want to find the x-intercepts, remember, we let y equal 0. For x-intercepts, y is equal to 0. So that means we have a 0 on this side of the equation, or on this side of the equation. Okay, if we look down here. So that's a 0, and we've got it equal to this fraction. But the only way a fraction can be 0 is if its numerator is 0. So that means the numerator, 3x times x minus 1, is going to have to be 0. And the only way that can happen is either x itself is 0 from that first factor, 3x, or x itself is 1. And so we end up with the two x-intercepts, x being 0, and of course y is 0 if we have an x-intercept. Now that's the origin, and that repeats what we already had here. The other x-intercept, of course, is when x is 1 and y is 0. So we can plot those points on our coordinate axes. And we'll do that in a second. Okay. Whoops. Actually, I have some slides missing, don't I? Oh my goodness. Well, I have some slides missing here. Let's quickly look at this, though. You'll have to bear with my drawing skills freehand like this. Yeah. Oh man, I'm sorry about that. We know we have an a vertical asymptote at -4 by looking at the denominator there, don't we? So let's suppose that this is where that -4 is. So we have a vertical asymptote there. And as I draw that, and play like it goes through there. Okay, I apologize. And when x is +3, we also have a vertical asymptote because that causes the denominator to be 0. So this is where 3 is. And what did we say? We had 0, 0 is both a y-intercept and an x-intercept, and 1, 0, which would be roughly here, is a x-intercept. Well, I feel pretty bad here about what's happening. because I'm going to run into some trouble trying to make this look nice. But let's do one other thing here, and just to make a point of it, is that we notice in this function, because it is in reduced form, that the degree of the numerator and the degree of the denominator are the same. And if that's the case, then the horizontal asymptote is simply y equal to leading coefficient over leading coefficient. Well, here the leading coefficient's 3, here it's 1, so y equal 3, that horizontal line is, and that we'll say is roughly right there, that horizontal line is the horizontal asymptote. So what we would need to do next is decide, we'd need to take some value out here like a positive 4 and decide where the graph is. And so we could put a 4 in for x and calculate y. Let's see what we would get. If x is 4, then y would be equal to, let's look right up here. Let's look right up here. 3 times 4 is 12. That's the 3 times x. And 4 minus 1 is 3. That's a 3. Divided by 4 plus 4, which is 8, times 4 minus 3, which is 1. Right? And so that's 36 over 8. 36 over 8, which is, what, 8 goes into 36 4 times? Yeah, 4 times. I believe it's 4.5. Check me out. It's 4 point something. It's 4 and 4/8. Yeah, 4.5, so 4.5. So that's our y value. So that means it's up here someplace. And just as we've already kind of discussed before, that gives us the idea that the graph looks something like this here. Okay. Maybe we need to choose an x that's in here, like a -1. And when we do, let's get rid of this ugly writing of mine. Make this look a little better here. Okay, if x is -1, see, what am I doing? I'm choosing an x value between this x-intercept and this vertical asymptote. And when I do that, and here's the reason. Does this graph go down here, or does this graph go up when we get close to this vertical asymptote? Okay. And we've got other issues as well, but we need to know that. Okay, so when we check out y, we just put it in the function, put -1 into the function, and so we'll have 3 times -1, that's a -3, times -1 minus 1, which is a -2, divided by our -1 plus 4, which is a 3, times a -1 minus 3, which is a -4, isn't it? And so that gives us what? A +6 over a -12, which is a -1/2, isn't it? So the graph is actually down here. So what we know is the graph, whoops, that's really ugly. It's been, oh, I'm sorry, but it looks something like that there, doesn't it? Now, what we've got a little work to do in here, and it is a little bit of a problem, okay? We've got several things. We could, what happens to this graph? Does it go up and then back down? Or does it just go back down and then up? I mean, you know, it's going to have to do one of those, isn't it? So we could decide, look, it could come down here and then go back up and then go up from here. It would probably be easiest if we choose an x value of 2. Remember, this is where x value is 1. And I really feel bad. I really do. I apologize. What I'm going to do is I'm going to calculate the value of y when x is +2. I think that will tell me a lot. So I'm going to let x be +2. Remember, that's about right here, right here. And when I do, let's see what we'll have. The numerator will be 3 times 2, which is 6. I'm looking right here, times 2 minus 1. So we'll have a 6 for the numerator. And the denominator will be 2 plus 4, which is 8, times 2 minus 3, which is negative 1. So that's a negative 8. Now, we can simplify that. Of course, that's negative what? 2 3/4, negative 3/4. The most important thing, though, is it's negative. So right in here, the graph, the y value is negative, so we're going to have a point down here. So what that means is that we can't be going up here. One right here, that means it had to go up above a little bit and then come down. That's really ugly, but I hope that you get the idea. And then we're going to do something similar out here. We're going to choose something like an x is equal to negative 5. You'll appreciate the next problem a lot because you'll see some nice graphs instead of the ugly things that I've done. Well, I'm choosing an x that's out here. And when I do, I'm going to calculate the y, and I'm going to get what? Negative 15 times negative 6. Oh my goodness, that's a positive 90. And down below, I'm going to have a negative 1 times a negative 8, which is a positive 8. The deal is that's more than 10, isn't it? And more than 11, in fact. It's 11 point something. Okay, but it's positive. So that means that our graph is way up here. So that's going to tell us that this graph is going to look like that up here. So in real, well, I'm going to stop while I'm ahead. Again, I apologize, but you get some idea, and if you were doing this on paper, you could do a much better job than I have here. Okay, well, let's look at the next problem. Here, the giveaway is in the title. We're going to graph a rational function that has a hole in it. But when we look at this function, we don't anticipate a hole in it. I mean, we don't think that immediately. No, the way we'll find a hole in it is when we start doing the graphing, the factoring to make sure it's in reduced form. Whenever it's not in reduced form, that's going to tell us that there's a hole. So as we look at the factors, we can see that, oh, well, there's two things that go on. Remember, this is the function. This is the function. And in this function, we see that the denominator would be 0 if x is either negative 2 or positive 2. And so the domain is the set of all x's such that x is not equal to either negative 2 or positive 2. And of course, the next thing we're going to do is we're going to actually say, oh, well, we can reduce that. But remember, we can't lose track of the fact that x is not allowed to be positive 2. And when we cancel that factor, we could lose track of that. So we need to put out there that x cannot be positive 2. Now this function looks like 2x minus 1 over x plus 2 as long as we don't let x be positive 2. And when we look at the function in that form, it's easy to calculate the y-intercept and any x-intercepts. And we've been through that before. To find a y-intercept, we let x be 0, and we'd get negative 1 over positive 2, which is negative 1/2. So that's where this point comes from. Just let x be 0, put it in here to calculate the y. Now, how are we going to find the x-intercept? Remember what we do? We let y be 0. So this side is 0, and the only way this fraction can be 0 is if the numerator itself is 0. So when we solve 2x minus 1 equals 0, we get the value x equal 1/2. And so the x-intercept is 1/2, 0. We'll plot those here in a second. Okay, now this is the form we're looking at right here. We're graphing that, but we've got to remember that x can't be equal to positive 2. We're looking at it in reduced form. And so when we look at that in reduced form, we look at this denominator, and that's what's being set up here. we can see it has a vertical asymptote at x equal -2. What causes this denominator to be 0? So x equal -2 is going to be where we have a vertical asymptote. Okay, and we can look at this and see that the horizontal asymptote, since the degree is 1 and the degree is 1, the horizontal asymptote is going to be y equal 2 over 1, or just y equal 2. And that's what I said here. Remember, we're looking at this function, and the degree of the numerator and the degree of the denominator are the same. So it would be y equal leading coefficient over leading coefficient. So here's our y equal 2 horizontal asymptote. Here's our x equal -2 vertical asymptote. Here are our two intercepts that we decided we were going to plot. And now we begin to think a little bit more. Okay, we think about, well, what can happen? So we're at this point. Let's just consider this point. When we come this direction, we can't go up at this vertical asymptote. We'll have to go down. And it kind of looks that way anyway, doesn't it? Kind of looks that way anyway. And when we're going this direction, we can't come back down. We have to keep going up, okay? And we've got to get close to this horizontal asymptote. So we can kind of get an idea that this graph's going to look like this right here, okay? But we need a point or two to the right, to the left of this vertical asymptote to find out if the graph looks this way or this way. So we plot a couple of extra points, and that's really all I'm saying here, keeping in mind how we're doing the calculation. So I've done that. I chose a -3. I got that value. I did choose a couple of other points out here, an x equal 1 and an x equal 3, and calculated the y's that went with those. And that kind of gives us a better idea of what this graph is going to look like here and what this graph is going to look like here. But we have to be real careful, because remember, this restriction still applies. X can't be equal to 2. And here's where x is equal to 2. So that means we can't have a position on the graph that represents that. So when we go to draw these pieces in, we've got to remember that that point can't exist on the graph, because that's the value of x that we can't allow, besides x equal -2. And so that's where the hole is, and don't forget to include that hole. Well, I think this is, although it's gone rather quickly, I think it's given you an idea of how you should approach these. Remember, try not to use your calculator except maybe for calculations. Don't graph it, because there's a good chance on your test you'll not be allowed to use a graphing calculator when you're asked to graph or determine and analyze the graphs of these rational functions. It's an analysis that's important, not how we punch them into the calculator. Well, good luck on your homework, and we'll continue the next time.